yes, if as I show you this screen, this is Ernest publication behind his prize, Nobel Prize. This guy,
yeah,
you see, Hasselman, is it? Hasselman.
Yeah.
Hasselman, yeah, Hasselman, and he published this paper in 1976, and very obscurely, they published in the non-physics journal, and certainly not mainstream physics journal. It's called, but now became their milestone. The first one, so it's called Tell Us. Tell Us, yeah. Tell Us is actually focused on meteorology community, and so. But the idea I discovered, what I have discovered last week is that he actually introduced an idea called the stochastic analysis, modeling, into the climate change. So that is a pioneer contribution in that field, and I think that is the main reason he got Nobel Prize.
I see.
So he's as he admitted, he dreamed to win the Nobel Prize in physics when he was younger, and obviously he became researcher in the 60s. So by this time he wrote this book, this paper. He's about 40 or something, about 40.
Here we go. The evolution of the distribution is described by a Fokker-Planck equation.
You notice that? Have you heard of that?
I have, in regards to the idea of a PDF changing.
Well, just few comments. His idea is not his original idea. So the stochastic modeling is not his idea. And I tell you what, something very interesting. He's getting closer to my original research area. In term of that is can we just add some? Can we annotate that? So basically, this is idea. So stochastic idea is not Einstein. It's actually we mentioned the two big names. Do you remember? One is the P.W. Anderson.
Yes, more is different.
Yeah, Anderson. Another is Japanese. It's called Kubo. And these two persons. So one made his important paper in 1953. Another, Kubo, also dealing with a similar phenomena, published paper in his early paper in 1954. So eventually, and this idea became what we call the linear response theory. Linear response theory. So the system they are started is not climate, of course. And what is this study is it's called magnetic resonance, MRI. I mentioned that. So both of them study the. So what happens? So when you have the sample, so when you measure, perhaps let's go stop here. Let's go to the whiteboard. Let's draw a much better diagram. So so this that is two guys. So there's the importance in application is that so one is a P.W. Anderson. Another is Japanese, Kubo. And his contributions 19. I just give you the timeline so you know there's some background. 54, and next 53. He's 1 year earlier. And that's another one is 1954. Now, what happened before that is that the discovery of NMR. So there's NMR. And that is NMR is referred to nuclear. Did you mention that before? Nuclear magnetic resonance. That is for short. So the full name is actually resonance absorption. So sometimes you have to put absorption here. So what does it mean that? So basically, the third one, we probably can explore more about the third guy who got Nobel Prize. He actually got half. He got the main part of this prize. And this phenomenon was discovered in just immediately after the war, about the not 14 but 1956, something like that. So after war, they discovered that, and in my field, is slightly different. So this is my field. That is called electron paramagnetic. Not magnetic. So I probably give some background. Paramagnetic. So the special magnetic resonance. And that's called this was actually discovered earlier by the former Soviet Union scientist in again after the war in 1944, 2 years earlier than the Enigma guy. Now in both cases, and they are dealing with the spin. Okay, so we have electron. We have electron. We have nuclear, like proton. Actually, there are the three fundamental particles in material science. In material, fundamental proton and a neutron. Okay. Now these three particles, we know that they have charge. They have negative charge. So this is electrical charge. And for the proton, they got a positive charge. For the neutron, have no charge. So these three elements can be used to constitute, to make up any atom, any molecule in the physical world. So this is basic particles. So of course, in addition, and after Dirac, they also have people discovered that, actually Dirac discovered that. We'll talk about this guy, Dirac. And in his theory, he predicted that electron has spin, which is a half. Okay. Now, this is just a quantum number, but the spin is just, and that's just like, so you just imagine that object can self-rotating, like Earth. Okay, it's called the self-rotation. But this you see, this is just one, how to say, is a primitive way to describe the property of electron. Actually, you cannot see that rotation. The spin is you can visualize that spin by just consider the spin is actually rotating. Okay, just like Earth. So our Earth follows the sun, right? This is the sun. And our Earth is also self-rotate every day. Can you see? 24 hours. Oh, we use our new time. We use our new time. You see? That's okay. So that is an analog. Okay. Remember, an analog is so important. So we always use analog by energy of something with something. But this picture, so this picture is not necessarily real. Okay. This is just analog. So this is spin. So the spin that is this analog. So you can see that is a spin is how to visualize. Okay. Sure. But eventually you have to accept that the spin of electron, or by the way, spin of the neutron, spin of proton are the same, half. Wow. Isn't that strange? So these are the quantum numbers. Quantum numbers. So we describe property of a small particle by using their quantum numbers. So these quantum numbers just discovered by Dirac, and they found that this electron has this strange, it's called intrinsic property of the spin. In other words, this property is just persist by these particles. Okay, and by the way, these three particles are called fermion. Okay, so this is part of our ingredients or whatever is element to make up everything. So these particles are called fermions. Fermions. So this is so that's after Fermi, after Italian Fermi. So anyway, that's in this category. Or to cut the story short, so what is NMR? What is EPR? So that's EPR. EPR. Okay. And so that is basically if you have a sample. So that's what I did that in 90s. Okay, I started to that 90s. If you put the sample, could be liquid, could be solid, right? So there should have many spin, and so if in this case, can I just use the arrow to describe the spin, right? And that is spin here. That is just use arrow. Okay. And so if without a magnetic field, so that is why we have magnetic resonance here. We have actually put the magnet, strong magnet. So this is the North Pole. This is South Pole. We have put the magnetic field here, so that the spin will take alignment, because like a compass. Okay, they make the alignment. So what happens is that if you just apply another, that is idea of the this is based on the linear response theory. Yeah, I think this will be useful for you to know the complex system, how this idea was originally developed. So basically, if we just use the RF source, like the we just make the R wave input, this kind of input, right? We just disturb. We just use the flashlight, kind of like a flashlight. Of course, it's radiation. We just use RF radiation to disturb this system, and the system will respond. You see, the subsequent response. The response, if you measure that in old fashion, and you will get something like this. So basically, if you scan and a certain, so this is intensity. And this intensity absorption, so this absorption intensity of absorption. This is in the form of energy. So the energy come and they will absorb something. So if you look at this, this time I use mu now. Mu for frequency. Okay, it's a very important idea. Mu is for the frequency. So we have choose particular frequency here. So this is mu null here, this is mu null here. And then what will happen is that around this mu null, we will see the peak like this. You can see, this is just like a statistic distribution. Okay, and of course this is center. This is center. So this whenever you see this, that is called absorption. So this absorption have a profile distribution. Okay, of course, sometimes you will see that for different system, this weakness or the in terms of statistics, you can say that the standard deviation or variance is changed. Can you see that? So depending on the spin in a different material, so this spin can either be, so spin is very important. So this spin, these are the spin. This spin could either be electron or nuclear, depending on the range of the frequency you use. So my field is in the electron spin area, which have used microwave. Okay, but if you start in nuclear, if you start a proton, then you just use a radio frequency, that's like our mobile phone, this frequency. So these things is an important idea now. This is called the spectra. So whenever see that distribution, so you remember this is an important idea. We're going to use this, we'll use analog of this idea. So whenever you see that one, so whenever, so this is called intensity, as a function of frequency. Okay, if we whenever say use this distribution, this is called the spectra. Okay,
it makes me think of the frequency. Makes me think of the Fourier that you were talking about.
Actually, today, yes, I say that is why I'm going to mention the Fourier transform. This is very important. See, because I can go further. If you see in this case, yeah, I think that's that's in my attention. I suggest you to pick up the Fourier transform knowledge, because that piece of knowledge will be enable you to understand the Hansel's math ideas to modeling complex system by introducing the. We're going to mention that now. So if you just in this case, the impulse, the input here can be simply can be written as can be described as a time-dependent impulse. So you could just have the short pulse. Can you see? You just had the short pulse like this. Can you see? You just switch on and switch off immediately. Switch on, switch off. The pulse. Can you see? So this pulse can be considered as input. So this input, right? And the signal you determine can be categorically called response. Can you see? So you can see the linear response theory is actually come from this idea. If I draw the diagram, so in general, the idea of the linear response theory is such. So you have a system, a black box, or complex system. Could be anything. Could be the human system. Could be the atmosphere. Could be anything. So it's like semiconductor. Okay. Oh, by the way, the third guy who actually started get Nobel Prize this year is also studies the spin. This studies spin in groups. He's not studying single spin, but studying lot of spin at the same time. So I heard the idea of the spin wave when I was just graduated from university. Actually, one of the professors actually drew my attention that do you know that there's spin can form the wave, because he's retired, he almost retired professor. He just trying to draw people's attention to the young people that there's there's potential research topics which might be very essential and also very important. The spin wave and spin gas, and these are relevant. Spin wave is just talking about the propagation of you can sort of impulse, okay, in the material which possess a number of spin, not just single one, especially in the magnetic. In the inferior, we can talk. Oh, there's another background. We can talk. Yeah, propagate. Yes, that's right. And the magnetic is very important research area, and a lot of Nobel Prize get Nobel Prize by studying magnetism of material. You see, magnetism has been a classical subject where people study compass with after discovery electromagnetism. They're just trying to explain why some material behave differently in the presence of magnetic field. That is a non-history. Okay? It's non-history. Well, to cut this story short, so what is a linear response theory? So basically, they depend this idea. So that's they say they have impulse. Can you see? I probably use consistent color. So you use impulse or disturbance, right? You just talk to someone. For example, you call someone, okay, in the crowd. You say, "Hey, hello, Smith," and people. So person who name is Smith, or who is calling, right? You can see that response. That's the response.
It's like a exogenous shock.
Just you got the impulse. This impulse could be selective or white noise. That is we'll talk about this later. All right, that is could be this is called impulse. Okay, impulse, input. So input. Create to import. Yeah, called import. So import. So import could be the selective. You call someone's surname, right, or first name, and some people pay attention to you. Like you have the school assembly, right? Someone is just focus on the principal's talk, and suddenly someone shout at someone's name from behind. So the guy who will be all turn on. Can you see? That's called a response. So that is called a response. Do you see?
Yep.
So this is called a response. So that is very keyword here. Response. And so these theories that they just assume they're trying to build up the theory on this. Okay. Of course you can first analog we can invoke is a amplifier, right? You can this could be or filter. Okay, this could be the filter or could be amplifier. So you've got input, you got response. And I mentioned I'll talk about what is a white noise. Is that you just call everybody at the same time, right? You call everybody at the same time, and everybody got the mobile phone, and the government sent the message to everybody. Say have you got the vaccines? They send the message to everybody. They go, they got all get the response, right? So that called
Sorry, does white noise just mean a uniform distribution over frequency?
Well, that is called white. Yes, that's called white kind. You see, if this is selective, this is called the selective impulse. This is called selective. And another impulse is like this. Can you see? So they just it's just they got everything. You got you can also select this. You can also that is something we have mentioned now. If you draw this impulse and response together, then you will see that how do we differentiate what is a uniform. So this impulse, okay, and so this is impulse, not the response. So this is the response. So this type of response. When talking about we measure, so we do some measurement, response, and that will be the input. Okay, I put it side by side so you can compare as input. Input. So that is the idea became behind this abstract research modeling now. When you start clamping modeling, whenever you introduce these ideas, so you have to understand what they're trying to do and what they can do. Okay, what they can obtain. So in this case, if you convert that, so that is a Fourier transform. Can you see this is time? After Fourier transform, I just use FT in the Fourier transform. So that's very important. Fourier transform. Yeah, that's short for FT, right? FT. So after this FT, we regard this selective. If you have one is a non-selective, okay, non-selective. A non-selective will be like this. You say you got a certain range. Can you see red color? So that you can select particular range, right? However, if you got white colors, that's why if you call everybody at the same time, you get this white distribution. Can you see? So this is the white noise. You can call the white noise white input. So this is white. You know, because it's white, and this is frequency because we use a mu, not f. In high school, use f, but in research we use a mu. Okay, so sometimes we school. So when you see this is a uniform distribution. Can you see? This is called the uniform distribution. Uniform. Do you agree?
Yep.
Uniform distribution. So that is how to characterize your actually my drawing is wrong. This is non-selective. This when you see the peak, it's non-selective. Okay. But of course we're talking about that. This is in the time domain. We'll talk about that later. So basically, if you want to call one body, one person, then you just use this range. If someone will respond, okay? Or you can say any surname between S and T, and they will turn to you, right? But if you just call everybody from alphabet from A to Z, okay, everybody will draw your attention, okay, attention. So that is a different disturbance. So sometimes they call this impulse. If impulse is weak, you can call it disturbance or perturbation. Can you see? These ideas come from the associate. They're all associated with impulse. Okay. Now, why linear? Can you answer this question? Why put the linear adjective? Why do we put linear response theory? We have talked about the linear theory since last year. Why do we call linear response theory?
I assume because the frequencies the are additive. So like my guess would be,
yeah.
Let me get my pen. If you have, I don't know, say something like this, and then you add in.
Yeah, additive. Yes, that's superimposed, right?
Yeah.
You can superimpose.
Yeah.
So therefore, so that is nature is response. So response you can, if you use R, if you use R for response, that can be written as a response of a different response. Okay, additive. Yes, that is a typical feature of linear response. So and besides, to achieve this linear approximation, it is actually approximation, as we discussed on several occasions. You know, Markov transformation. You have to assume the disturbance is weak, and any response could be considered as linear. Okay.
Yep.
So if you change some variable and you expect that, so if you monitor that response, and you will see that can we just go next page? So if you in this time, if you keep doing this disturbance and continuously, not continuous, okay, you can do some measurement by just disturbing the system, okay, and consecutively, right? After every second, I just disturb, and during which, if you just call just one person and only one person getting response, but during the time you will change the frequency. So actually that singular. I will talk about the input. How do we describe input now? So basically, I'm talking about the linear. What is linear means that is very important idea. When we started the response, this time we just keep doing this response, right? And we just keep doing that disturbance, okay? And you will eventually get something like that. You will get a response, okay? Response like that, okay? Response like that. And eventually, of course, if the person getting tired, the response is a decrease. Okay, pay no attention. You see, just wolf. You know the children's story. The wolf is coming.
Yeah, exactly.
Yeah, the wolf is coming. So getting retired. So therefore, the response might be time dependent. Okay, and so the responses are. So you have to say, well, this is a curve, right? You can see that. You form the curve. So in general, you would expect that response would be curve, non-linear. Okay. Yep. So this curve must be non-linear, right? The curve is non-linear, non-linear. However, after you have started calculus, you know that if the time interval is short enough, can you see? There's delta t here, right? So we can always use this approximation by just assume that this is linear, can you see?
Is this the response for one impulse, or is this repeated impulse?
That is consecutive, could be not just because time dependent. You see, another thing we have to study that is how the people these play. So these can say, when people getting aware, they get listen, they pay attention to you. That is called, this precipitation is, so this, let's do that. So this period is called excitation. So people get excited, okay, or probably they can absorb something. But after that, then they were getting tired. That's called relaxation. So you will, from time to time, you will start relaxation. So this is some ideas behind this response theory. You got impulse, and either people getting excited or they getting tired. They eventually after or eventually they get how to say, saturated, and they will just drop. So the response will decrease. You see that?
But I have one question about this.
Yeah.
So if we imagine that, say, for instance, this is
You can draw the picture. Yeah.
One person's response.
Yeah.
Is let's call that I, and this is nonlinear, but is the R equals.
Yeah.
So if this plus this plus this, this is the linear part, but this is nonlinear.
Oh, I think this whenever encounter in linear, that you will see that because the basically see the do you remember the Taylor series?
Mm-hmm.
Taylor series.
I suppose my question is this the entire system, or is this one component of the system?
Well, it is overall response.
Okay.
Overall response.
Yeah.
You see, the basically any function, so including R function, okay, can be written as if you introduce how to say, if we know if that is depend on the certain property. For example, the delta, right? We use a small delta. We use this small delta. So it's a function of something. And according to Taylor theory, you can always separate them as 1 plus and a delta and plus delta square. And there has some coefficient. See, there's some alpha, beta coefficient. Can you see that? So any function, any response function can be written as a sum of the many different polynomial. So this is a polynomial. Can you see?
Yep.
And polynomial. So in the first part, this part is called linear. You see, this part is called linear. And this part is called quadratic, right?
So that's the approximation.
Yeah. So okay. You can consider Taylor series as approximation. If you, because Taylor series say any function x, right, can be written as the sum of many terms. Can we just go to use Ri, I from 0 to infinity? So that is how to appreciate that whenever we introduce a theory, we say it's a linear theory, which means that it is just as approximation method.
Right, but
only pick up the response, the linear part of that response. Yes, go on.
If you just go back to the other page, maybe I can just
this page. Yeah.
We have a let me get my thing. So we have our system, which is made up of a bunch of stuff.
Yeah.
And then we have our impulse come in, and then there's some function on this, and then it comes out, and we have our output. And our output.
Oh, we call it response. Can we stick it with response? Otherwise,
response. And then this is R, and then it's time dependent.
Yeah.
I suppose my question is, does the linearity refer to this Taylor series, or does the linearity refer to the fact that it's this plus this plus this plus this of the?
Oh, you have to go back to that the idea of measurement. So the reason we can get a response because we can measure that. It's called measurement. These measures, MEAMENT. So we are talking, well, you have imagined we'll do some experiment. We measure something. Of course, if you can selectively measure individual element in the system, that's fine. But in many cases, because the system is too complicated, at most we can get the overall response.
Okay, sure. Okay.
Yeah.
Yep. Okay, I understand.
And I think we don't mix up with the how to say rigorous or analytical theory and the approximate theory.
Okay.
So basically, they are wonderful. Okay, these I just return to. So these two guys actually they are wonderful. They actually apply the linear response theory to discuss the phenomenon. So basically, what is happening is that if you go to, if you have to mention some quantum physics now. So if you just talk about this phenomenon, how can this system possibly, in this case, this is a special system, okay?
Mm-hmm.
This is a system where the spin can have two energy level. That occurred to the spin system only, not necessary for climate, you see?
Mm.
So that is original idea is that if you apply a magnetic field, this is in this which they got many spin, okay?
Mm.
And many spin, they are many like spin, okay?
Yeah, not
so
much
these spin
personality.
are not, have no personality, okay?
Mm.
They just behave as you know, that people in the communist country, it's called a like spin. The like spin is can be very just follow. So if you have so this vertical is this is energy. So this energy level. So this energy level, I think we eventually we'll put this picture together, and we're talking about a Boltzmann distribution now. Can you imagine? So if this is energy, so therefore, so some spin will stick here, that can be spin up and spin down. Okay, the perversity is stable. Other spin will get excitement. They want to do business. They want to investment. Okay, they jump up. They jump up. So therefore, as a whole, do you remember that they will follow the Boltzmann distribution? You see that they're following the Boltzmann. Talking about the population different. They're called the Boltzmann distribution.
So the energy, I see. So the energy is actually a function of the component's spin.
A number of spin. The number of spin, because each spin represents a particle. Okay, you have. I think to really appreciate, to understand, if you want to use this, 2021 Nobel Prize in Physics as an example or as a textbook to learn a complex system, then you have to get familiar with what is a spin. Okay, except the first guy, because the first guy just used this idea to apply to atmosphere. But unfortunately, the basic interaction in the atmosphere is uncertain. Identity is unknown. Identity is uncertain, right? So for example, whenever they talk about, the deep ocean water will be evaporate, okay, due to the warming. But they just imagine, you see. They don't know how that would happen, okay, given.
Is it fair to say that a lot of the stuff in complex systems, they've taken very simple models of collective behavior, like the Ising model, for instance, and then they, with very low personality.
Well, I wouldn't say the Ising model is a primitive. The Ising model is very intuitive. It's very great idea. So you see, that's come to back to the philosophy now. You have being a good researchers or being a good physicist, you should be capable to actually simplify things without missing the essence. So that is important thing. So Ising model, I wouldn't put it into the same basket as the climate study.
I suppose what I'm saying is the Ising model is great for what the Ising model does, but the complex systems people, they use it as an analogy and they extend it past.
Yes, it's quite dangerous. It's unreliable. We're talking unreliable. You see, as I always say to my students, when you study physics, you will find that we not only to pay attention to the connective or statistics behavior of system, we pay attention to the fundamental interaction in the first place. We know, how actually Boltzmann's law were derived by just assuming that the spin have the particle have preference to stay in the lower energy level. You see,
ab initio, right?
That's right, ab initio. I see this is you see this they just, I think I make some remark and recently I think the Norwegian Nobel Prize Committee trying to replace the modern physics since Galileo by the Aristotle's physics. That's just for general remark. I don't know how many people can understand what I'm talking about. So basically, modern physics is strongly based on experimental evidence. And so each state, no matter whether you're talking about, quantum statistics, or they are based on the behaviors or interaction among the particles. We know that interaction. But unfortunately, nowadays, people just pick up this idea, or actually, this theory, just like, Hasselmann, he introduced this idea in physics. Actually, that's my main point today. And he introduced this idea is called the linear response theory or stochastic model, and in the community of the meteorology, that's in the middle 70s. But actually, this method, this theory has been applied successfully in the magnetic resonance to explain. I will draw the diagram now. So to explain that can we just finish this one?
Sure.
So this next spin, and so without disturbance, they are very happy. So they are very happy. But if their disturbance come, so there is disturbance as input, or disturbance, what you call it. So then they will get excited, and also these disturbances just have the particular frequency. So this frequency will be just match that this condition. Can you see? So imagine this is a simple system where the spin can only choose. They have two choices. They can either stay up doing business adventures, go to Shanghai, or they stay at home, like gardening, watch the footage. But these are just natural distribution, without disturbance. Now all of a sudden they got input. For example, you can investment. You can watch the Shanghai index and you do some investment. So they become excited. So therefore, that is a condition. This is called the resonance condition. I will have to. Can we call it resonance? The impulse can be non-resonance or non-selective or resonance. So we have the resonance.
And white noise is non-selective.
Or non-selective or reason or non-resonance. Or non-resonant, resonant, sorry. If it is a resonant, then they will satisfy the resonance condition. You see right down here. So this is important. So there's a resonance condition. Just like call particular person's name is condition, resonance condition. Or group name, any surname starting with S will respond, So that's how to select the people in a group. So under this condition, I have to write down here. So basically, you have this quantum statistics now. So we have the H multiplied frequency. So that's input. Can you see? That's I wouldn't call it H null. I probably just call it F in. We're talking about a different notation in this consistent way. So if according to the quantum theory, if that is this energy, this called energy difference in energy interval, can you see? If that satisfies this condition, if they said you can persuade with you can just I recently watched a lot of the advertising to ask people how to use particular software to do investment. They are trying to mapping the potential investor. If their interest and their habit, the way and the objective is matching that condition, what do? They react. Can you see? So they will jump up. They will jump up against the odd of the convention. The family say, don't take a risk. They can take a risk, right? And they go up. Let's go to Shanghai. Go to to do business. So that is exactly what is called excitation. And these conditions very important. This is a condition. To even we can make it simpler by saying that in this case, that is input. I use this old fashioned again. I think I have to make it consistent. I use mu, not f. Because that is very. If we want to talk about these issues,
instead of frequency.
We use mu. We use mu. So in this case, I just rewrite that condition. Simple condition, very simple. You see, physics is so simple. So in this case, we have. I mean, the basic formula is so simple. So that's not the intermediate. I can tell you. And the guy, the Hasselmann, actually, he's at the beginning, we can actually, after we study Fourier transform, we can go to his original paper. Okay. So basically, this is that's input, we're simply equal to delta E. Okay. Now delta E, you can just rewrite delta E as the frequency in terms of frequency. That is a mu. That would be the mu. No, okay. You can call this mu is intrinsic, or people's habit, people's inherent property, and the way of thinking or whatever. So this is so basically, if this equation, if we use this notation, we can simply say that resonance condition can be simply written as this. Can you see? Okay. Of course, the thing is that, okay, for example, all of a sudden, okay, the government intervention occurs, say, we're not going to buy Australian coal, and then that impulse will disappear. Okay, so this will cause someone to return. So this is called relaxation. Do you remember? Yep. They will return to the conventional way of thinking and and behavior or action taken. So we return. So that is a example, actually. Well, of course, this is in the presence. I can still have to use this notation here. The formation of this interval is due to apply the magnetic field. Yeah. Okay. So if you're mapping, if you measure, so if you do some measurement, this is response. If you want to do the measurement, what you can see that this will be, this is just my diagram now. So you got, I put them side by side, okay? So this is, they're all in frequency domain, okay? They're all in frequency domain. So we're talking about distribution. So this is, this is input, this input. This is a response, okay? So you will see that something happened here. So if the impulse is aware of that one, if that's impulse, if this impulse is aware, for example, the impulse is just in this region, all right? And in this case, there's no response. Can you see? There's no response because these, remember, they are all behave connectively. No individual, no personality, okay? So if you apply the things which is far away from this one, there's no response, you see? So this is what we call, this is called, this is a mu null. That is a characteristic property of the spins, okay? So they are not interesting. For example, if you say, oh, investment return is 200%, okay, and people don't believe that, okay, and you say, oh, investment return is just 0.5, less than the deposit interest. People have no interest, okay. However, they say, well, if they say, well, if it just generates impulse by peak of the frequency, can you see in this region, can you see what will happen? That will satisfy this condition now. So zero response, can you see? Yep. Zero response.
And is this peak, this is the resonance?
This is resonance.
Yep.
This is resonance. So this is a resonance response. You can call it resonance response. And so all this is a real system in physics, okay? Yep. In actually, we that's why we're talking about that. These are, by the way, give you another idea. Actually, if you read that the stochastic modeling, actually they take it for granted that they use this terminology. So this is called the 9 shape. This 9 shape, right? The shape. So the 9 shape can be very narrow, you can see. like as narrow as a delta function, you see? So the narrowest distribution will be like this, can you see? If this is almost like delta function, you see? Or it could be like this one, like where the how to say, this distribution have a very large variance. Okay.
Yep.
And this process, this phenomena, so this is a phenomenon in experiment. So basically, this is observed, experimentally observed. This observed response, okay? And so return to the first two hero here. One is Anderson, one is the Tubal. So what are their contribution? Their contribution is just to treat this phenomena as a stochastic process. So that is the keyword, stochastic, stochastic, or random. Stochastic process. They have a process in which that this spin and this spin, they have their internal affair. They interact with each other. They are family members, so they have to make the decision by negotiation, right?
They interact.
They interact. You see, they are not just all of a sudden, say let's do or not do. Okay, they have the. So this process and this interaction, this just like a spreading of consensus, is random. It's random. So therefore, they can nowadays when they talk when you go to the public media report, they say, oh, they use a random walk, they're drunk, whatever. Any animal, indeed that is so. But actually, what does it happen? So if you want to know the process, but today I just give you some background of why we have why do we have to learn Fourier transform? That is the purpose, Casey. So the stochastic purpose, I think I don't want to go too further. You can. It's just the name. Stochastic is just random. Okay, random is random. So how do we? The important thing is how to treat this random process. Now here I give just the two formulas. So two formulas, and we'll talk about that in detail. So one is you can treat this change as a periodical change. Can you see? That is an essential formula we can use. It's omega A. Yes. So this is you can use this formula to describe almost any change variation. But in this particular case, where A is a periodical, you see, we are interested to discuss a periodical motion. That is the context where we introduce the Fourier transform. So where A is can we write A as A? So that is A null multiply. You can use a complex number, or you can use a sine function. Can we just use a sine function, which is more familiar for you, right? So in this way, that is A is a periodical variable, periodical variable. And in the weather, in the climate, in the context of this weather and climate, many things are periodical. I think at some certain stage I mentioned that my opinion is that the change, the so-called climate change, just be part of the resultant periodical change. Okay, so we return to that idea soon. So basically, if you consider this is but this is in this case, it is a deterministic, right? Yes. No stochastic, no drunkards. Okay, and we see the sunrise from east every day. And you can predict for next centuries. You can
perfect sine.
Your perfect sine wave. So tell me, what is this omega? Can you guess? Do you remember what is it? Yeah.
Noise?
No, it's not yet. Not yet.
It's
if you have noise, we wouldn't be able to. If the influence on noise is strong, and wouldn't be able to predict the sunrise. You see. Okay. Is it deterministic? This is deterministic.
Is it amplitude?
Yeah.
Amplitude?
not amplitude. This is amplitude. Yeah, we can talk about some basic. This is amplitude. Yeah.
I don't know what the omega is then.
And omega is determined by the period. It's called the angular frequency. Angular frequency is something to do with the frequency. And to be precise, the omega will equal to 2 pi mu. That is simple relation. So omega is double, is just the frequency multiply the frequency. So it's just constant. Okay.
Okay.
We have to go to some basic of math now. If you see these functions, see these you have the sine theta. How to draw it? Is a sine function? Yeah.
It is a sine function multiplied by a constant, which would be.
What is the maximum value? Do you remember what is the max value of this y?
Is it between these two?
Yeah, that is 1
yep.
and -1. Yeah, that's right.
Yep. And then this would
then you have the periodical. Yeah, we make it periodical. Expanded. Yeah.
So it would be if it was like this. With the theta.
Yes, that's right. Yeah, right. Yeah, right. Okay. Okay. Yeah, different amplitude, right?
Yeah.
This is different amplitude. Okay. This is when amplitude when A is larger than 1. Okay, that's right. Yep. So to be exact, can we just draw one more time? So can I draw a more regular display? That matter, you can keep that. You can keep that. You can keep that. That is a part of your learning. Yes, that's good. Okay, you can keep that. This time I just draw more. Yeah, you can recover that. So you can. So basically, you can. I just draw your attention that when you have this, how can we end up with? How can we describe periodical change by using sine function? So in this case, you can keep your drawing there because this is part of the. You can. There it is. Undo. You can undo. So yeah. I just draw more precise, and so we can get some relation out of that graph. Oh, that's my hand. And so on. Can you see that? So in this case, can you label this number? Can you, if I write 2 pi here, can you follow me? If I write 2 pi here, it's a pi, because for the sine function, so the sine theta, it's a periodic function, because every time if we added the 2 pi, not any angle, but 2 pi. So sine theta plus 2 pi will be the same, you see? You cannot tell the difference, we just added the 2 pi. So this 2 pi is called the period, you see? So this term is called the period.
See, I thought the period was, this would be.
So what is a periodic function by definition?
It would be like this.
Yeah.
2, not 1, 2, 3. So this is 1, and then this is another.
The period you can call this is a period. So this distance period.
Okay.
When they repeat, that's right. You can you can use this called the peak to peak distance.
Oh, peak to peak. Okay.
Peak to peak distance. Okay.
Yep.
But of course, this notion of the period is focused on this particular form. You see. Now our form is slightly different. In our case, you can say theta in our case is equal to product multiply the time, t for time. So we have constant over here. Okay.
Yes.
So how do we so there is a simple relation. So that's why basically this relation tell you all. If you want to go to detail, so this is a relation. So basically the omega over here, that is in high school we spend a lot of time to discuss this constant. So this omega here primarily that is these equations come from this fact that 2 pi divided by t will equal to omega. Or you just write the other way around so you can see. See, omega will equal to 2 pi divided by the period.
Yep.
So because frequency, so when we count the periodical change, we can either use a period, right? You can either use it's called a period, or you can use the frequency. Is a frequency. So when we start a periodical motion, we can either use period and frequency, but there's a simple relation between these two constants. The t is and they are reciprocal. You see. Or the TV equal to 1. Can you see the product?
Yep.
Just how? Okay. Yeah, you can think that's what that means the periodical variable. So for example, you can either say there are there are many, for example, there are 360 sunrise per year, right? Or you can say that the sunrise every day. So these two notions description are the same. One is that we're given a time interval, you count how many times the phenomena repeat. That is in 1 year. In 1 year, the sunrise, every day. They just talk about the same thing. The sunrise from east every day. You see, you can either say the period is 1 day, or you can say the frequency is 360 over 1 year, which is 1. Does that make sense?
So that's a very intuitive way of putting it. I've never, okay.
Yes, this is just how to count the periodical motion. Okay, periodical motion. And by the way, I think today I will just give you another formula. So these frequencies, this omega, this is can we call is omega 0, okay, can become disturbed or can be influenced by what we call the random change in frequency. So the frequency, this is just equivalent to say that the actual frequency we observed can be as written as the sum of the natural frequency plus the disturbance. Okay. So this is random. You see, this is random or stochastic.
Yep.
Okay. So this quotient is called the random frequency. So this is called the random frequency modulation. Okay, or random, you can random frequency modulation. This is important idea. The randomness means that the average of this guy will equal to 0. Okay.
Yeah.
But their contribution to the measured frequency is not necessarily 0. Doesn't that make sense?
Yes, it does. Yes.
So there's a whole idea of the stochastic process is based on this random frequency modulation, not random walk, but just the frequency will be modulated or changed. You just like you play the music, right? And you play the C, kick C, and all of a sudden the composer will written added the D or E. It's called the modulation, right? The changing.
Changing
that
key.
Makes it
Changing
out of tune, right? Out of tune. But of course, it makes the sound. It makes the music more colorful, right? I use this musical analogy to understand. Well, so basically, what happens is that the so-called the stochastic modeling is just deliberately to introduce a random variable whose statistical mean is 0. However, their effect, their influence on the response is not necessarily 0.
And you think
that is the key.
this is a more intuitive way to build up the idea of a stochastic process, as opposed to starting with Brownian motion and then from going.
That's right. This is just, they're trying to say, they just tell people a story in more quick, in a more efficient, economical way. But yes, we can stop here now. So basically, yeah, sure. This introduction to the linear response theory, yep. And behind that is a Fourier transform. Fourier transform is just a tool, okay? But also, yep. It's very, very powerful tool. There are no other ideas better than Fourier transform in this context.
Awesome. Very, very interesting.
All right, we'll keep this talking, and I will read. We probably will mention the third guy because he certainly studied magnetism, ferromagnetism. So where the spin have, they call the spin frustration. So you have to, if you just trying to invoke a quantum physics, and you have this random or undecided frustration. It's called frustration. Okay. Okay. Anyway.
Cool.
Okay. Well, we'll stop here and see you next time.
All right. Bye, Dr. Young. Thank you.
Goodbye.